Hopefully everyone had a nice weekend, nice Halloween. Any questions about where we're at in the course, how we're doing? Anyone getting ideas for the final project? Again, there's still time, but what we have, how many weeks left? This is week 10, so maybe 6 more weeks, and it tends to go fast. So be thinking about, again, a project of math of blank, and you fill in that blank. So, and again, it's very open-ended, you be creative. Actually, make it fun. Make it something you're already doing. Could be, if you make things with your hands, that involves geometry, math, anything, and feel free to talk to me about it as you have questions. Good. Let's see. Do I have... So we're going to get into advanced probability. So we're following up. What was our... let me see if I've got... Where is my writing thing? Oops. My little... Here it is. This will do. It's not my favorite tool, but it works when I want to write. I'll put it over here. So what was, when we were thinking of probability, chance of something happening, how do we calculate a given probability? Involved a fraction, right? We're dividing two things. What are the two things we divide? So the total goes down at the bottom. That's total number of things, so it's just counting them. And what do we divide into? The number of the event, the good thing, whatever we're looking for, right? So I'll just put number of events, number in the event, whatever we're looking for. So if it's like flipping a coin, it might be how many heads do we get out of so many flips. So basketball, how many times do you shoot a free throw? How many times do you make that free throw? So total would be how many shots. The event would be how many times you actually make it, or maybe how many times you miss it, whichever you want. So that's what we're going to work with, is that our probability involves really just counting the items and then dividing. How many total do we have? We call that a sample space, if you remember. So tie in a little bit of vocabulary. So that sample space was all the things that could happen. We counted them, and the event, this was how many times that particular event that we're looking for. Okay, so this time we're going to look at things like having two events, something happen, and what's the chance of it happening either a second time or a second thing. So this will also involve something called conditional probability. Sometimes we know what already happened, and again, if it's drawing a card out of a deck of cards, sometimes it can't happen. If you've already drawn the Queen of Spades, you can't draw it a second time because it's already been drawn. So we'll see how that works. And then we're also going to get into something called odds. These are different than probabilities, but they measure the same thing, but they do it mathematically in a different way. It's just a slightly different way. But we're going to hopefully prevent the mistake that I made, was I treated odds and percentages, probabilities, the same way. And so if you go to the racetrack and you're thinking in terms of probabilities, the racetrack thing is actually done with odds, and so we'll take a look at those. Let's see. Maybe we will. Here we go. Yeah, here we go. Oh, that's why I don't like this. I have to clear it off. So first of all, we kind of talked about this last time, and this is kind of a very formalized formula, but if I say there's a 60% chance of rain, what would you tell me about the chance of not raining? Perfect. That's what this whole page says. It means there's anything happening is 100%. So if you take a particular event and you know its percentage, you know its percentage for happening is say 25%, 75% not happening. So it's all, there's like a complement, right? So that's all it's saying is this one that they're subtracting from. So that represents 100%. That's why I like to use percentages. And so we're just subtracting probability of rain 60. Subtract that off. The probability of not having rain is going to be 40%. Okay, that's as simple as that says. But on top of that is sometimes it's easier to calculate the chances of something either not happening or happening, but you want to know the other one, and sometimes calculating it might be more complicated. So sometimes go for the easier calculation and then subtract it from 100 if you need to. Okay, it might be easier to calculate what's the chance of it not raining, so you do that. But you want to know what's the chance of rain, you subtract it from 100 and you got it. Okay. And so they do like this. So we've got a deck with 52 cards. The probability of not being drawn a queen, well, we know that there are 4 queens. So instead of trying to count all the things that are not a queen, we got 4 queens. 4 out of 52, which is 1/13. They reduced it. So you subtract it from 1, or 100%. So there's 12 out of 13 ways to not draw a queen. Okay, so that's an indication where you don't, I need to count how many cards are not queens. Although maybe that wouldn't be too hard, 4 from 52. Okay, so far so good? So this is then, there's going to be 2 types of probabilities we look at. These are going to be, the first one is going to be the OR probabilities, and then we're going to look at AND probabilities. So remember, OR probabilities are sort of the inclusive OR. It's either this or that or both. So OR is the inclusive side. When we get to the AND probabilities, that's sort of an exclusive. It has to be both. Okay. So what happens with the probability of A or B happening, I'm going to roll a die and I get a 2 or a 3, is simply we add them together. Okay. Probability of getting a 2 is 1/6. The probability of getting a 3 is 1/6. So the probability of getting a 2 or a 3 would be 2/6. Again, which reduces to 1/3. So we just add them, as long as they're what we call mutually exclusive. And what do you think that word means? What's mutually exclusive? They can't happen together. So they're if one happens, doesn't mean the other. So they're it's a Venn diagram that looks like this. There is no overlap. You either get a 2 or you get a 3. You don't get something that's partially a 2 and partially a 3. Because we'll look at, there's times when that could happen, and we're going to see that it's the basic same thing. We add the 2 probabilities, but what we have to do is if they aren't mutually exclusive, which means they're kind of a place where they overlap, we're going to subtract that. So simply, if there's an OR probability, what's the probability of this or that? Think we're going to add them together. But as we count, we just have to be careful. And so here's one, getting a king or a queen. Is there a card in the deck that is partially a king and partially a queen? No, they're mutually exclusive. You either get a king or you get a queen. So that's 452 plus 452, 8 out of 52, which is 2/13. Okay, so that's just add the probabilities individually. Understanding mutually exclusive, the easiest way to do it is to find something that's not mutually exclusive, and that's going to be our next example. Is we notice it's the same. We still add the 2 probabilities, but what we're going to do is we're going to subtract the intersection of the 2. Okay, and again, this doesn't, it's got all this notation, but let's look at the example and it becomes clearer. I use this one because that's what the textbook gave us, but so we've got a group of 25 baboons, and we're told that 18 enjoy grooming their neighbors, 16 enjoy screeching wildly, and 10 enjoy doing both. So if we randomly were to choose a baboon, we could get one that likes both of them, right? That there's this overlap. So we want to find the probability that it enjoys grooming its neighbors or screeching wildly. So we have to kind of figure out what's going on. We could use a Venn diagram. That's one way to do it. How many like doing both? Remember when we did that? 10. So that goes in the middle. And then we'll call this side grooming. So G for grooming, and this one for S for screeching wildly. How many would go in the grooming part over here? Close, but notice what do we've already got? 10. So what do we put here? 8. So that the whole circle has the 18. So see how that works? Remember, we had to subtract off. And then the same thing with the screeching wildly. There's a total of 16 in the circle. We've already got 10 in there, so 6 are going to be over here. What this allows us to do is to see, well, when we go to calculate this, since there's 25 baboons, bless you, what we're going to do is that the ones who enjoy grooming, there's 18 of those out of 25, so that's that probability. Those who enjoy screeching wildly, there's 16 out of 25. But what did we do with these in the middle? We've counted them twice here, haven't we? We counted them with the grooming, and we also counted them with the screeching wildly. So what we have to do is we have to subtract them one time, and so this one, we're just making sure we count each thing one time. Because otherwise, these 10 in the middle, actually, if we just add the two probabilities together, we end up counting them twice. The other way this is not the only way to do it. We could have also just said, well, there's 8 here, 10 here, 6 here. So we could have also said 8 out of 25 of being in this group, 10 out of 25, and then 6 out of 25. And you'll see we'll get the same answer with both of these. This one we get 24 out of 25. This one we get 18 plus 16 is 34, minus 10 is 24. So they both end up at the same probability. So I guess there's just one baboon who doesn't like to do either, right? That's what we came up with. So again, with this concept, you either just carefully count and make sure you're only counting everything once, or you just don't be so careful. Count this group, and then subtract the overlap. Okay, so that's OR probabilities for you. And it's whenever you have something that could be two things. Thinking of a deck of cards, how might this apply to a deck of cards? What characteristics could we look at of a deck of cards that an individual card could have actually two of the different characteristics? Say the queen, like a queen. It could be a queen, right? What else could a queen be? Or what else does a queen have? How many types of queens are there? There's 4 types of queens. So we could also be talking about suits, right? And I think that's the next example. Maybe the queen, or drawing a club. That queen is also there's at least one queen that's both a queen and a club, right? So we have to end up, again, just being careful how we count whenever we're doing things, say with cards. And so yeah, here they worked it out for us. And they did it kind of like I did both ways. Well, actually, yeah. They did it the one way. Okay. So I guess that's the other slide deck I use is that it talks about a card, probability being drawing a queen, probability of drawing a clubs. There is an overlap, so you have to take off that one. As I spoke earlier, we're going to take a look at something called odds. And odds are similar to probabilities, but what do you notice that we've got two kinds of odds in favor of something happening, odds against. What is not in the denominator with an odds that is with a probability? The probability, we count how many events we have, and we also count a total. Notice with odds, we don't count the total. We count how many are in the event and how many are not in the event. And what this comes is for sports betting primarily. There's your teams either win or they lose. I guess there's a tie, but a lot of times when they calculate the odds, they just count wins versus losses, right? They don't use the total. They compare wins to losses or losses to win. So wins to losses would be the odds in favor, and losses to wins would be the odds against. And again, it's just a numerical amount. When I do odds, I like to do it with the sort of a ratio type thing with the colon rather than doing it as a fraction. Because what could happen with this kind of a fraction? Could you have 10 wins and 2 losses? You sure could, and you get a number that's more than 100%, right? You get 8. So these are not percentages, these are just a comparison between wins to losses or losses to wins. But notice that the odds in favor and the odds against, they're just the reciprocal of each other. Okay. So if you win 10 times, lose 2, then the odds against are going to be 2 to 10. And again, sometimes they like it this way, but I like to write them as 2 to 10 because you see this as now being an odds. And again, if you start looking at that and say, well, that's a 20% chance, it's really not a 20% chance, because how many total games does this involve? If I lost 2 and I won 10, how many games did I play? 12. So our probability, what we have to do, it ends up being, you add the 2 together, and then in the top. So this was actually, as a probability, it's 2/12. Whereas a odds, it's looking at 2 to 10. Okay, so we just make you aware of those because, again, in certain situations like sports, and again, sports betting is now legal. It used to be illegal, but now it's legal, and it's all over the place. And they're going to give you the odds, but sometimes they might list it like a fraction. And if you do the mathematical calculations as if it were a probability, you'll be a little bit off, and you might think you have a better chance than you really do. Okay, so just know that odds is something different than probabilities, although they're both measuring the same thing. I guess it's like using the metric system or the inches and feet. Okay, so okay, and again, we could, like with rolling a die, I don't like the way they do the calculation. I like to, they're doing calculate the probabilities and then divide the probability of the event divided by not the probability. I would rather just still do it as a count. So the probability of, if the event is 2, then it's, instead of being 1 to 6, what it is it's going to be, there's 1, 2, there's 5 numbers that are not a 2. So that's how, we still can get it by counting, but the things we're counting are different. We don't count the total, we just count how many are in the event and how many are not in the event, and that's going to give us our odds. Okay, we can turn it to a probability because we add those 2 together, and we can get our total relatively easily. And that's what they're saying is, if you know the odds, you can get to the probability. if you know the probability, you just, again, we could do a subtraction, we could get to this. So we can go back and forth between them, but just know that they're different. So we've got that example. We're going to do the last one, which is an and probability, but we're also going to bring in conditional probability, which I sort of alluded to last time when we had that table. Okay. So the thing here with and probabilities, this and this happening, we have to say that there's two things that are going to happen. You're going to flip the coin twice. You're going to roll the dice twice. So there's a first event and then a second event. This is how these always happen. And so what's the probability of A happening? Sorry. A happening and B happening. That's when we multiply the events, the probabilities together. Okay. As long as they're called independent events, which means one does not change the probability of the other. Okay. And we're going to see, we'll look at some examples to see that when things are not independent events. If I flip a coin, is the second flip dependent or independent? Does it matter if I flip a heads and then I'm going to flip it again? Does that coin know whether it got a heads or tails, so it's going to be different? I don't think so. So it shouldn't change. Okay. So here's independent events. There's a roulette wheel. There's 38 numbers. Right? 1 through 36. There's 0, 0, or 0 and 0, 0. They have some colors. There's 18 black, 18 are red, 2 are green. And then it wants to know what is the probability of red occurring on 2 consecutive plays. Okay. So what's the probability of getting a red? 18 are red out of 32, or wait, out of 38, right? And which reduces to 9 out of 19. So probability of getting it the first time is 9 out of 19. When we do the second spin, the ball doesn't remember where it was. It's, as long as it's independent, we just multiply the probabilities. So the probability of getting red twice in a row is about 22%. Okay. So remember, when we have an or probability, this or that, we add. When we have an and probability, we multiply. And then the only other thing we have to consider when we have a and probability, independent events, again, repeatedly multiplying. Again, we'll go through the quiz together, so we'll see some other examples. But this is probability getting a baby girl is a half. Probability getting 9 girls in a row would be 1/2. So that's 1/2 to the 9th. And again, you would say hurricanes. The thing is, it's hard to tell. If you live in South Florida, is having a hurricane one year, is it really independent? Maybe it is, maybe it isn't. I'm not sure. So again, we'll look at some examples from the quiz. But then there's other things called dependent events, where the first thing happening actually changes the probability of the second thing happening. And we're going to see that happens. One of the places we can think of is we're drawing from a deck of cards. So if we draw one card out, how many cards are left in that deck? It had 52, but if we draw one out, there's now 51. So our deck is different. And that's the idea behind dependent events. Okay. And so you'll see this one. It's kind of wordy and such, but you want a trip to Madrid, and you don't speak Spanish, but you want somebody who does. You've got 10 cousins who want to come. And let's see, how many, let's see. They tell you that 3 of your cousins can speak Spanish. So find the probability of selecting 2 Spanish-speaking cousins. So you've got 10 cousins. So the first draw, there's 3 of them that speak Spanish, so you have a probability of 3 out of 10. But on the so you choose one, and let's say they speak Spanish. How many names are left in the hat? 9, and only 2 of those names will speak Spanish. So the probability of getting the second one is 2 9s. It's no longer 3 10ths. So that's the idea between a dependent, is that the first event actually changed the probability of the second event. Okay, and so you'll see that that's whenever you're drawing things out and not replacing them. And again, we'll look at some examples in the quiz. And again, another example. I want to get it to the conditional probability. That'll be the last concept thing we need, and then we'll look at the quiz. Okay, conditional means that we know something has already happened. And so we sometimes will look at an event like, say, what's the probability of B happening assuming A has already occurred? So what's the probability I'm waiting, my friend's going to show up for coffee because we had this appointment, but I know it's raining and I know he doesn't like to drive in the rain. So that, if I know it's raining, I'll say my probability will be different. He's less likely to be there. If it's not raining, maybe he's more likely to be there. Okay, so conditional probabilities, having some kind of knowledge about something, gives us changes the possibilities. And we will look at these types of problems are oftentimes used in a table, but we'll look at this one. So we're going to select a letter randomly from the letters of the English alphabet. There's 26 letters in the alphabet. Find the probability of selecting a vowel given that the outcome is a letter that precedes H. So what that does is we're not doing it out of 26 letters because we know that it's in the first, well, how many letters precede H. Now, precedes H does not include H. So that means it could be A, B, C, D, E, or F, or G. 1, 2, 3, 4, 5, 6, 7. So we have 7 possibilities. How many of these are vowels? How many vowels do we have in 2? A and E. So 2 sevenths. But notice it's not, if we didn't have this given, this condition, we would be thinking, well, it's out of 26, and how many vowels? There's 5 vowels, I think. So we have a 5 out of 26 probability without that condition, but we've got this condition. So usually it's written as given. Okay, so it means and again, it's just, it sort of directs us how to do the counting. Yeah, they also go for this one. This is one sort of example we were looking at. We've got a table, those with breast cancer, no breast cancer, and whether they got a positive or a negative mammogram. We've got totals over here. But watch how this one works. Assuming these numbers are representative of all U.S. women age 40 to 50, find the probability that a woman in this age range has a positive mammogram given that she does not have breast cancer. So the way that works is we take the given, she does not have breast cancer, and we ignore all the other data. So the given, when we have a table, we're just looking at this column. So now we want the probability that the woman has a positive mammogram. That's 6,944. Given that she has breast cancer means we're only dealing with this group of 99,000. Notice we're not looking at this, we're not looking at that. We're just looking at those that have no breast cancer. And that would be our probability. So that's how we can calculate a conditional probability with a table. And they walk you through. And again, this PowerPoint is available in the in Canvas in the first little module part. So you can take a look at that. And we're done. So it's now time for what? Quiz. Get some homework done, right? So get half of your work done. Okay, so let's go ahead and look at the homework quiz, and we're just going to apply these concepts for the most part. But we'll find out if we missed anything. Got two. Let's see. Homework quiz. Here we are. Okay, let's go ahead and start it. Let's see, how many questions do we have? We've got 5 questions. So let's start with question 4. Let's see, let's make that a little bit bigger. There we go. So a 6-sided die is rolled twice, so there's 2 rolls. Let E be the event, the first roll is a 2, and F the event, the second roll is a 2. Okay, so we're rolling it twice. Are the events E and F independent? Whether you get a 2 on the first roll, does that change your probability of getting a 2 on the second roll? Good. No. Oh, wait. It doesn't change the probability, which means they are independent. So sometimes these questions are. So the answer to this question actually is yes. They are independent. Actually, I'll go ahead and enter that in because they don't interfere with each other. Now it wants us to find the probability of showing a 2 on both rolls. And so do you remember do we add or do we multiply? 50-50 chance. There, we roll a 2 and a 2. What's that? That's the or, because we're at this or that could happen. When we have 2 events happening one after the other, this and this, that's going to be a multiplication. Okay, so we're going to have how many 2s are on the dice? 1. How many numbers are on the dice? 6. So it's 1/6 times 1/6 would be the probability of getting a 2 followed by a 2. Now you might think that's also the probability of getting a 2 followed by a 3, right? But sometimes there's different things have the same probability, but this would be our probability. 1 times 1 is still 1. 6 times 6 is 36. So getting a 2 followed by a 2, the answer is 1/36. Okay. And again, you might have a different question, but even if it was a different number than 2, it's just there's only one of those. We're good. Okay, so and is going to be multiply, or would be the addition. But notice how they kind of ask this. Okay, and again, we go through this, and if they're asking about dependent or independent, that's an and probability, right? This is happening, that's happening. So let's see this first one. Lacey draws a diamond from a deck of cards. Without replacing the first card, she then draws a second card and gets a club. So she's doing 2 draws, but doesn't replace them. Are they independent events? No, not in this case, because if you don't replace that card, the deck is now different. It's only got 52. So good. So they are not independent, which means the probabilities are going to change. So now determine the probability of drawing a diamond and then a club without replacement. So how many diamonds are there in a deck of cards? 13 of each suit, and there's 52 cards. So that's the probability of doing that. Now we draw out a diamond and we don't replace it. What's now going to be the probability of getting a club? Well, how many?
13 out of, yeah, 50.
Good, 13 out of 51. That's, it's a slight difference, it's a slight change. And then we can multiply those two. 13 times 13 is 169.
Why are you saying 51?
What's that?
Why is it 51?
Because we didn't replace the card. So now we took one card out, so now the deck of cards only has 51 cards in there.
Oh.
So kind of think of the process it's going to. And the next one's going to say if we replace the card, then it is independent, because each time we draw we have 52, right? We've kind of restored the deck. But in this case, we get 169 out of, what's 52 times 51? 2,000? 652. Okay. Good. And I think we just enter that in as is, 2,652. Draws a diamond from a standard deck to 52 cards. She returns the diamond to the deck and maybe shuffles it. They don't tell us that, but since we've returned it, there is now 52 cards again. This is independent because it's been reset. And so when we calculate this probability, even though it's kind of the same sort of events, get a diamond and then a club, since we have restored the deck, it is 13 out of 52 the first draw. The second draw is also 13 out of 52 because we replaced it. So for dependent and independent, if you don't replace the card, you're changing the probabilities. That's dependent. If you do replace the card, it's like having a new deck, and then that makes them independent. And again, the numerator's the same. It's 162 or 169, because that's 13 times 13. But now we've got 52 times 52, so the denominator is 2,000. Anyone helping me with that one? 52 times 52.
Oh, it's 2,704.
And 4. So we see the denominator is actually bigger. Let's check the answers.
You have to put
Oh,
a
it's in
decimal.
decimal.
Oh, they want me to actually. Why they make us do so much work? Okay. Okay. I'll do the first one, 169 divided by 2652. And how many? 4 decimal places. Okay. So if you divide that 0.0637, that's 4 decimal places. And this one, 169 divided by 2704. That's 0.0625. Yeah. Okay, so we had the right values, but they just not in the right way they wanted them. Okay, does that make sense? So dependent, independent, a draw and then another draw, the and probabilities, we multiply them. And again, it's really with the probabilities, you just carefully count. It's 2 questions. Question 3. So we're going to draw 1 card from a standard deck. And as we see with this one we have an OR probability, the probability of drawing either a 2 or a king. So in these type of OR probabilities, what do? Multiply or add?
Yeah.
This one is the one we add. Good. So what's the probability of getting a 2? Well, how many 2s are in a deck of cards? There's 4, because it's not the suit, out of 52. And then how many kings are there? 4 out of 52. Again, we haven't drawn any. We're going to just draw one card, and we either get a 2 or a king, and those are both successes. So it kind of makes, hopefully it makes sense that we could think of it, there's 4 2s, 4 kings. We could really just add them because either one's a success. It's 8 out of 52. Okay, and they want a reduced fraction. 2 goes into both of these. 2 goes into 8 4 times. 2 goes into 52 26 times.
Yeah.
And then now 2 goes into both of these. 2 goes into 4 2 times. 2 goes into 26 13 times. So 2 13ths. And thank you guys for reading and getting me to remember to read what they want. Determine the probability of drawing either a 2 or a diamond. Now what do we have to watch out for here? 2 is 4 out of 52. How many diamonds are there in a deck of cards?
13.
There's 13 out of 52. But is this going to give us a right answer? What about the 2 of diamonds? What did we do? We counted it twice, right? We counted it in the 2s and we counted it in the diamonds. So what we do is we subtract off one of those. Okay, so we counted the 2 twice. So there's a 2 that has both. Again, or we just carefully count. So, I've already got the 2 here, so I could make this 12 out of 52. You'll see you'll get the same answer. 4 plus 13 is 17, minus 1 is 16 out of 52. 4 goes into both of those, so you get 4 out of 13 as a reduced fraction. Let's check our answer. Got them right. So again, the OR probabilities, we're watching for mutually exclusive or not mutually exclusive. So if there's some kind of an overlap, we just want to either count very carefully or subtract off the overlap. That's all we gotta. So question 4. This one will get us into conditional, but it might not always, you know, we got quite a few things here. So table below shows the number of survey subjects who received and not received a speeding ticket in the last year and the color of their cars. So we got red cars and not red cars. Some got a speeding ticket, some no speeding ticket. So we've got our totals over here. So find the probability that a randomly chosen person has a red car. What numbers would we use for that?
295.
Good, 295, because that's the total that have a red car out of the total of number surveyed. Again, your numbers may be different, so that's going to be 295 out of 662. And again, this one, they don't really tell us how they want their answer, but I think we could probably do it with just the... And when I do my answers, I would prefer not to reduce the fractions, again, because it's easier to see from the table. How about has a speeding ticket? Well, there's 374 that have a speeding ticket out of 662.
You did one of them decimals.
You do? Oh, this is not a decimal. Oh, thank you. So just again, read the things that they say. They want a decimal. Yes, thank you. Which is actually nice. I get tired of when they're asking for reduced fractions, because, so that is, they don't tell us how many decimal places, so we'll just do 4. Usually this thing doesn't bother if you have extra, but it might give you problems if you don't have enough. So a speeding ticket, there was 374 that had a speeding ticket out of 662. So far these are just straight probabilities like we did last week. And for that I get 0.5649, but there's a 5 next to it, so I'm going to round that up to 10. But if I round it up to 10, then the 4 gets rounded up to 5. That's the only time when you do that. Has a speeding ticket given, so now we're into the conditional probabilities, right? We have a conditional given they have a red car. So for this one, we're only considering people with red cars. So we kind of just, we ignore all this other data. That's what the given does. So has a speeding ticket, there's 188 that have speeding tickets, given that they have a red car. The total we divided by is 295. Okay, but not the 662, because we have a given condition. We're just talking about the 295 people who have a red car. Right, so we've got 188 divided by 295. So a conditional. .6373 when I round it up. Has a red car given they have a speeding ticket. So now let's get rid of some of this stuff. What's that? No, because it's backwards. So this was have a speeding ticket given they have a red car. This has a given, so the given part changes. So this given is that they have a speeding ticket. So what it does is it comes this way. Now you're right, we're using the same red car and speeding ticket. We're using the same 188, but notice we use a different total for this one. The other one was going horizontally. This one's going with a vertical. So has a red car, that's 188, given that they got a speeding ticket, that's 374. And when we calculate that one, we get a different decimal. We get 0.5026. Does that make sense? So notice that this question, D, is this part here. The one before it was looking this way. So it's looking at this row. The D is looking at this column. So it depends on which is the given. Okay. And what I always like to do is I highlight the given and then go back there. Has a red car and got a speeding ticket. Has a red car and got a, so it's not conditional. It's sort of two things, right? And the and we have to look at, so it has a red car. It's 295 that have a red car and got a speeding ticket. So that's 188. But this is, notice there's no conditional, so we have to take it out of the total. Red car and a speeding ticket, both things have to happen. There's 188 out of 662. cleared out. It's 0.2840, rounding up. I'll just, yeah, down here, write it in decimal forms to the nearest thousandth. Well, I went out a little bit further. We'll see if we might need to take one off. Has a red car or got a speeding ticket. So or means we're doing what? Adding. Okay, good. Has a red car. See red cars, 295. Got a speeding ticket, 374. So we say 374 out of 662 plus 295 out of 662. Are there any though that we counted more than once? What about this 188? We counted them for red cars and we also counted them for getting a speeding ticket. So this is a case where we have to subtract off 188 out of 662. So we add these together, but we subtract off the overlap. So I get 374 plus 295 minus 188 is going to be a total of 481 out of 662. And that gives us 0.727. And let's see, I think that one's this one actually, since they went to thousandths, I'm going to round the 2 up to a 3. I'm going to just take off the extra decimal place there. I'll take it off there. And then 4, I'm going to round that 5 up to a 6 because they only want it to 3 decimal places. And hopefully I might still get one wrong. Check the answer. Oh, I liked them all. Okay, so this was kind of a mix that had some or, some and, some conditionals. That was question 4. Are we ready for the last one? Okay. So these are all conditional probabilities, drawing from a deck of cards. So two cards are drawn from a deck of 52 cards. Determine the following probabilities, and they want them written as a simplified fraction. What is the probability the second card is a heart given that the first card is a heart? Okay, so what do we know? So we draw a first card, we know it was a heart. What is the probability that the second's going to be a heart? Well, first of all, how many hearts are left in the deck of cards?
12.
There's 12 because we took one out. How many total cards are in the deck of cards? 51 because we didn't replace the card. And again, let's see. They weren't real clear on that, but I guess we just kind of have, that's an assumption we're going to make if we draw a first card and then they didn't tell if it was returned or not. We'll just assume it wasn't. So again, these can reduce. 2 goes into that. That's 6 out of 26, which is 3 out of 13. Okay. What is the probability the second card is a spade, given that the first card is a diamond? Similar type thing. How many spades would there be? Well, there's still going to be 13, right? But now, since we drew a card that was a diamond, there's one less, so it's out of 51 instead of 52, which is different than this first one. I don't think that reduces. In fact, I'm pretty sure, yeah, just don't. So it's 13/50 seconds. What is the probability the second card is a king?
Wouldn't it be 51?
Oh, thank you. Yeah. See, that's a. Thank you. You got to pay attention because I don't. It's always been my problem. I wrote it down right, but I didn't. What is the probability the second card is a king, given that the first card is a two of spades? Two of spades out there. Isn't it going to be really the same? Well, almost the same thing, but how many kings are in a deck of cards? 4. Two of spades comes out, so there's only 51 left, but it doesn't affect the number of kings. It's going to be 4 out of 51. And let's see if...
How did you get the 4?
Because it's asking how many kings. So there's 4 kings in a deck of cards. So we're focusing on that the second card is going to be a king. It could be any kind of king. So there's 4 of those. But this given part tells us one card's been taken out. It doesn't affect the kings. It affects only the 2s and the spades. So we'd say 4 out of 51. Let's see if I can do that. There we go. What is the probability the second card is a number card? Oh, now I gotta. Given that the first card is a 7 of hearts. So the 7 is a number card, right? How many number cards are in a deck of cards? Well,
48, because the aces aren't.
Aces are not a number card, right?
4 aces.
It's 4 aces, but a jack's not a number card.
Oh, yeah.
Queen. So there's a. So this is kind of where we do it backwards. So there's aces, king, queen, jack. So there's
36 number cards.
4 times 4 is 16. 52 minus 16 is 36. So out of the 52 cards, I counted 16 that are not number cards, right? That was easier to count than count all the number cards. And then when we subtract, we get 36 that are number cards. Okay, so there's 36. We've drawn one already, so there's only how many left? 35. And out of 51 cards, because one card had been already drawn. $35 divided by 51. Let's check our answers. Didn't like our first one. The probability the second card is a heart, given the first card is a heart. Oh, did I do that? I did 12 out of 52, didn't I? See, it's really 12 out of 51, right? So I messed up there. This should be out of 51 because we've already drawn a card. Yes, there are only 12 hearts, but there's also only 51 cards. I think that actually makes it easier because it doesn't reduce. 12 out of 51. Yeah, it still didn't like it. Does it? Oh, maybe it does reduce. No, 2 can't go into 51.
Oh, it's 4/17.
Okay, because
51 divided by
3 goes into both. Okay, see, you learn these things. I don't think I can change it, right? Because I've already done 2 changes, so hopefully.
Yeah, it's 4/17.
4/17. Okay, thank you.
Wait, what was it supposed to be?
Well, 12/51s reduces because
Oh, okay.
I didn't spot that 51, if you add it, you get 6, so
I said I did the-
yeah, you can divide both of these by, that's why I don't like this. I would rather just do the decimals, because, anyway, so that 3 goes into 12 4 times, 3 goes into 51 17 times. Who, yeah, who comes with that knowledge around? So, but all we need to do is 70% anyway, so we're good. But again, so that should give you a good basis for going through the rest of the homework. Again, the focus is we've got some and or probabilities. That's when we add and possibly subtract off the overlap. We've got and probabilities. That's when we multiply the probabilities. Or if it's a table, we just, that's how we pick it out. And we've got conditional probabilities where we know something already happened, so it changes the counting that we do. We already know something's already happened, so there's usually fewer things that are left to happen. And we just sort of do that, and again, the probability is just the number of the things that can happen or we're looking to have happen divided by the total number of things that could happen. And then they didn't have any odds in here that I saw, so I don't know if they will be in the homework or not. Sometimes they update that, but just remember odds are that's kind of important to know if you get involved in any kind of sports betting, because those are probably going to be odds. And just know that it's different than, the numbers are different than probabilities. Very good. Any questions? Okay. What we'll do, so Thursday is a open lab day. Come and get help with anything that you want to get help with if you want to. Next week we'll go into 10, which is some counting, which looks at permutations, combinations. So if we've got lots of things to count, so it's some organized ways of doing counting. It does relate back to probability. We'll do a few probability things with those counting, like for lottery tickets and stuff. In fact, if you want to do a little experiment, why not buy a Powerball? Maybe you'll come back and you'll be a billionaire next time we meet. Remember who your favorite math teacher is if you win. So. But I'm going to go buy a ticket. Sure, why not? Doesn't hurt to have $1 billion. Just don't. Thank you, guys. Thank you.